Okay, everyone, let's get started. Sorry, I'm running a couple minutes late here. So just to remind everyone, we have our next exam. Our next exam is on Monday, this coming Monday. It will cover all of Chapter 3, Sequential Logic. Hopefully you received the email notification from the forum on Moodle where I posted exercises from the book that you can use to study. Some of these exercises I've already incorporated into quizzes. Some of them I discussed in class. I'll cover a few more today in class. But these are the questions from the book that I'll use to build up the exam questions. So if you go through those and you feel comfortable with all those questions, then you'll be in good shape for the exam. Okay. And as far as the text goes, I got through all of Chapter 3, so everything that's in Chapter 3 in the book is covered. Okay. So today my plan was to do some review of Chapter 3 and begin Chapter 4, which is, in my opinion, is even more interesting. At the end of it's going to cover all of Chapter 3. So if I go through, I'll just quickly run through all the topics here from the lecture slides. So we started out by talking about bistable circuits. These are gates that are cross-coupled, that have gates, combinational logic gates that are combinational circuits that have cycles in them that form these bistable circuits. You have to be careful because it's not as simple as just taking some gates and cross-coupling them and have it form a memory element or a bistable circuit. It doesn't always work out that way. As a matter of fact, we even looked at an example that was not bistable, which was the ring oscillator. Yeah, this one. So in this case, this was actually a ring oscillator, and this thing oscillates. It's not stable. So the basic bistable circuit design is the SR latch, and the idea with this is that if R and S are both 0, which is this configuration, you'll end up capturing a value in Q, and then the complement of that value will be in Q bar, right? Complement. If R is 1, R is reset, and S is 0, S is set. So if you have a 1, 0, you'll force the Q value to become 0. And likewise, if R is 0, and I always get this backwards. If you reset it, R is 1 and S is 0, so that resets the Q to 0. And if you set it, which is where R is 0 and S is 1, you would set Q to 1, right? And then if you set both inputs to 0, whatever the last value of Q that you latched in there will stay, so it will retain memory. All right, and then 1, 1 is an invalid. If you put 1, 1 in there, I think you get. If you put 1, 1, then you get 0, 0 out, which is not really meaningful because it violates the the behavior where 0, 0. If you had 0 for Q and 0 for Q bar, then Q bar wouldn't be the complement of Q, right? So that's just something you would avoid that as in the design that uses this circuit. All right, so then the D latch was when you add a little bit more logic at the front end, at the inputs, that really doesn't do much aside from create this clock and D input, that in which the clock, whenever the clock is high, it will translate the R and S input into this as a 1, 0 for a 0D and a 0, 1 for a 1D. In other words, D is the value that I want to save in the latch, And when the clock is high, that value gets passed into Q. And then when clock is low, it will always force R and S to be 0, 0, because these are AND gates. Right? So when clock is low, I'll have a 0 in this input and a 0 in this input, and thus I'll always have 0, 0 here, which means the latch will enter the behavior where it will ignore D and instead continue outputting whatever the stored value in the latch is. Right? And then we then also talked about flip-flops, which is another... Yeah, the flip-flop is another improvement where you use two latches together. And this makes the flip-flop be edge sensitive. So instead of sampling D into the memory, instead of storing the input value whenever clock is high, its level is high, instead it stores it on the edge of the clock. So whenever the clock, generally it's the rising edge of the clock, although you could also, I think if you put this inverter on this wire instead of this one, you could make a falling edge flip-flop. But generally speaking, you think of them as rising edge active, but it doesn't really matter whether it's rising or falling. The point is that it captures the D value on one of the edges of the clock, and so you're going to update Q every cycle, right? Okay, any questions about that? Okay, so then once you've got D flip-flops, you can build finite state machines, which are sequential logic circuits that do something. Finite state machines have memory built into them, and they allow you to remember history. So you can build things like the traffic light controller that we had as an example, where the traffic light controller has a state. It can be it could be in one state or the other, and then it can transition. And in the traffic light controller's case, whenever it would transition from one street being red to the other, it would go through the yellow light phase. So it would, have these little, transitions that that changed over time, right? Does that make sense? Everyone with me? Okay, so then finite state machines are comprised of next state logic and output logic and the clocked portion, the memory portion. And when you design these, you design them as you design the behavior of a finite state machine as a graph. And each node in the graph represents a state that you could potentially, that the system could be in for one or more cycles. The transitions represent the activation of one state from another. So and this would happen on the edge of the clock. So when I'm in this yellow light state, when academic is yellow, the clock edge comes and I can transition to this state where academic is red and bravado is green. Right? Once you've got your graph designed, you can build your next state logic as a table. And in this case, you have an input for the current state, you have your top level inputs, and then your output is your next state. You have to also decide how you're going to encode the states with some binary value. There's really no wrong answer here. You can encode states however you want. You just have to make sure that each state has its own unique value. The number of bits that form the state, at a minimum, has to be the log base 2 of the number of states rounded up, although it could be more if you want to. I mentioned in class that if you encode states one way versus another way, it may make the next state logic more costly in terms of gates or number of inputs, right? But behaviorally, it doesn't matter how you encode the states. And then the output logic is just, in the case of a Moore machine, the outputs are a function of the state. And then in a Mealy machine, the outputs are a function of the current state and the input. So Mealy machines, think of it as more is less. Mealy is more in the sense that Mealy has this extra capability over a Moore machine where the inputs can update faster because they can respond to the inputs even within a state. So you can have different outputs for even one state, right? You can be in one state and you can have multiple outputs depending on what the inputs are. Does that make sense? Okay. We went through a few examples, and then there's the timing diagram is used to debug or validate the behavior of these circuits. We need a timing diagram because we need to know what state the system is over the course of time. And generally speaking, the inputs will be changing as well. So we want to be able to see the input versus time, the state versus time, and the outputs versus time. So in these timing diagrams, time is on the the horizontal axis, and you have ones and zeros on the vertical. The vertical axis is meant to look like a voltage. It's meant to look like an oscilloscope, like it's voltage. But a lot of times you'll see 1 or 0 in here, just binary. Or in the case of a multi-bit signal like the state, you'll have transitions and then just the state written in as kind of like a symbolic representation of the state value. Any questions about that? Yes?
Can you explain the basics of the clock, what it is?
Yeah, well, the clock is what controls the sequencing, right? So you think the clock is kind of, whenever you have a sequential logic circuit, the clock is, I always think of it as the heartbeat. It's really what moves data paths in a sequential circuit. Now, the clock is shown on here, but it doesn't really need to be shown because it's a little redundant, because all you really need to know is cycle 1, cycle 2, cycle 3, right? You know that the state is going to change at most every cycle, right? Sometimes it'll stay the same. Like in this case, the system was in S1 for 2 consecutive cycles, right? So there was no transition. But the state could potentially change every cycle, right? But the convention is to put the clock on here, and the clock is a square wave. Well, it's supposed to be a square wave, although in this case they emphasize the edge by showing the edge sort of as at an angle here. This is like when it rises, it's kind of at a slope. You can see it. So, but basically the clock is a square wave, and then the reset is also shown. And the reset is also a little redundant because it's really generally is just used at the beginning, just to reset back to the start state, right? So what is the purpose of the clock on this diagram? It's mostly just to know when I update the state, right? So if you're building, in fact, this might be a good time to go through an example. I had planned on looking at, let's see, the book has an exercise 3.22. Bring up I thought I had it. Oh, here it is. All right, so exercise 3.22. This one says, describe in words what the state machine in figure 3.69 does. Using binary state encodings, complete a state transition table and output table for an FSM, write Boolean equations for the next state and output, and sketch a schematic. So in this case, we're starting out with a state machine. And make it a little bigger so it's visible to everyone. There we go. OK, so we've got a reset state, and then we've got one output Q, which is 0, 0, and 1. It states S0, S1, and S2. And there's 2 inputs, A and B. Now, there's some shorthand used in here because A and B is a 2-bit signal. So technically, we ought to have 4 transitions coming out of every state to cover the 4 possible values of A and B. You guys with me? right? But we don't. In fact, some states, like this one, only has one transition going to S1, and then there's one loopback transition. So it's like, okay, well, there's a problem, because what happens with S0 with regard to B? Well, B is a don't care, so it's just not shown. It's kind of a shorthand, right? Also, sometimes you'll see these transitions, instead of saying A and B, this will say like 1X here on this transition, meaning that A is 1 and B is a don't care. You guys with me? So, but this is also kind of shorthand. This is saying if A is asserted, if A is not asserted, right? So the first question is, what does the state machine do? Well, just looking at it, you can see you start out in S0 when you reset, and the only way to get out of there is if A is asserted, if A is 1, right? Once you get to S0, if B is asserted, you'll move on to S2, right? If B is not asserted, you go back to the beginning at S0. And then A is a don't care, right? And then if B is asserted, you move on to S2, in which case you assert the Q output, but then you have an unconditional transition that goes back to the beginning. So once you reach S2, basically you assert Q for one cycle and then you reset. It's almost like you pulse. It's like a pulse of Q, right? So yes?
So is it at like the end of each clock cycle, it like checks what the state of those?
It checks A and B at the end of each cycle and decides whether it should, basically go forward or go back or stay in the state it's in.
Like when everything kind of updates.
Right, right. So what does this state machine do? Well, it's looking for a pattern. It's looking for it's got A and B inputs, and it's looking for A to be 1, and then it's looking for B to be 1 in separate cycles, right? And when that happens, it pulses Q and then resets. So it's kind of like a combination lock almost. It's waiting for A to be asserted, and then in a subsequent cycle for B to be asserted, right? Now, if A and B are both asserted, you can't skip this state. If A and B are asserted from S0, then you'll go here, and you'll get stuck here forever until you assert B.
You'd have to assert it again, though, right?
Yeah, it would have to go. It's so you have to say A, and it moves on, and it records. Okay, I saw an A. I'm waiting to see a B. And it'll wait there forever because, oh, actually, I'm sorry. I take that back. It won't wait there forever because if you don't get a B in the next cycle, it'll go back to start because of this transition, right? So actually, I screwed that up. It waits for A, and then in order to advance to the next state, you have to assert B in the very next cycle. It's a little bit more restrictive than the way I described it initially. So you have to give it an A in one cycle, a B in the second cycle, and then it gets here, it pulses Q, and then goes back to the beginning. So it's a little bit more restrictive. The only way to unlock this thing, basically, it's like I said, it's like a combination lock, is I got to assert A, and then next cycle's got to be B, and then like this Q could, for example, be a signal that unlocks it, right? If I do anything other than that, then I won't be able to get to this, accepting state, this Q state, which is kind of, by the way this is structured, it seems like that's my goal. I want to be able to get to here, right? Yes.
So does the not B, does that actually like a not B input, or does that mean like anything?
It means B is 0. Yeah. So A and B are always coming in.
So like if it pushes like a not A instead of a B or a not B, would it stay there or would it go back to 0?
No. It sometimes the loopbacks, depending on the style, are implied, but in this case they're not. You can see that it's not going to ever stay in this state there's no way to stay in this state for more than one cycle. Okay. It's impossible because you're either going to move on to here or you're either going to go forward or you're going to go back in the next cycle. You'll only be here in one cycle. Likewise over here too. You'll only ever be in this state for one cycle. This state, because it has this loop back, you could stay in here for multiple cycles. So this is kind of like your starting point, right? And it's kind of like the default state, sort of, right? It's kind of where you go when you haven't made any progress towards your goal, which is getting to this state, right? So that's kind of describing in words what it does. It's recognizing a pattern where A is asserted in one cycle and then B is asserted in the very next cycle. Okay, so we can come up with we could build this thing by creating a table, a next state table. The next state, well, first of all, how many bits do we need? We've got 3 states, so we need at least 2 bits that make up our state. So, sorry, state. So we have state, and then we've got A, then we got B, and then we got next state. Right? So, so there are a total of 4 inputs and 2 outputs, right? Why do I say 4? Because I know state's got to be 2 bits because there's 3 states. So I need at least 2 bits to encode the 3 states. And so if I build the entire table, I'm going to need 16 entries, right? And I'm a little too lazy to do all that. So I'm going to use the shorthand notation where I can specify don't care as in the inputs, right? And remember, I mentioned in chapter 2 that if you have a don't care in a truth table, the don't care in one of the inputs in a truth table, that don't care would logically expand to multiple rows, right? That satisfy all the possibilities, the possible values of the don't care value. You guys with me? Okay. Anyway, so state. So let's see. S0. I'm going to assume. Let's see. I'm going to assume S0 is 0, 0, and I'm going to only advance if A is 1 and B is a don't care, right? And in which case I'll go to S1, meaning 0, 1, right? If I am in 0, 0 and I get anything else, I want to stay in 0, 0. So if I get a 0x, then I'll stay in S0, which is 0, 0. Right? And again, and you might be thinking, well, how do you know that state S0 is 0, 0? I just assign that on the fly, right? Right? Okay, if I'm in S1, which I'll just say, which I've already assigned to 0, 1 based on this, I'm looking for B to be 1 and A to be a don't care to advance to S2, which is going to be 1, 0. Actually, I should make that 1, 1. No, 1, 0. And if I'm in 0, 1 and I get a x0, then I'll stay in, no, actually I won't stay in S1. I'll go back to S0. In that case, I got to go back to the start, right? And finally, if I'm in 1, 0, which is state S2, and I get a, well, I don't care. I don't care what I get. I'm always going to go back to S0, right? But this guarantees that I'll be in S2 for at least one cycle, because I can only trigger one of these transitions per cycle, right? So you might say, well, wait a second. I mean, you're not going to, S0 is kind of, it goes back to S0 right away, but yeah, it still stays in there for one cycle, right? And what that'll do is that'll pulse Q. Q will be high for one cycle, so it'll give me one, it'll give me a pulse there, right? Everyone with me? Okay, so so when you build the next state logic, then you can build the next state logic as a combinational logic circuit, just like we did in chapter 2, using this table. The only difference is that the outputs of this table, remember, are the next states. So the outputs are going to feed back into the inputs on the D flip-flop. So there's 2 D flip-flops that I need to store my state value, right? So for example, let's see. Oh, and I have to, because I have 2 outputs, I have to calculate, I have to build each one separately, right? So let's see. The good news is that it looks like I only have one row where the leftmost next state bit is 1, right? Does that make sense? Unless I'm not missing anything here, right? Yeah, right? This is 0, 0, right? OK. So good. So I really just have to take this and convert this to Boolean logic, that one row, right? So what is that? Well, if I assume that this is S1 and S0, let me give these S1, that's a bad example because we got states that are S1 and S0. Hold on. Let's say S sub A, S sub B represent the 2 bits of my state. Then I can build a circuit. This will be prime, sorry, prime. I can build a circuit for S sub A prime is going to be not SA, SB, and B. That's simple. You can't really simplify that anymore, right? So when I build this in hardware, I will have a flip-flop with a D input and a Q output. One of them will be S sub A, one of them will be S sub B, and the input for S sub A is going to be not S sub A. So this will be feed this back into an inverter. SB sorry. And B, right? It's bigger. Make sense? So I have a 3-input AND gate where I just take not SA and SB and B, and that's going to give me the input to this SA. This is going to be my next SA, so SA prime. Right? So it's just like building any other combinational logic, except you've got this feedback that happens from the current state to the next state. Now for this one, let's see. Well, that one's pretty simple too, right? Because I just have to look at this row for SB prime, the next SB, right? So that would be A. Oh, yeah. So again, this would be another AND gate going into here. This is going to give me my SB prime. And so here I'm looking for A and not SA and not SB, which like that. Look good? It's an inverter. And then Q is my output logic, and Q is asserted only when I'm in S2, and S2 is state is when SA is 0 and SB is 1, correct? Yeah. Sorry, SA is 1, SB is 0, right. So when SA is 1 and SB is 0, that is my, it's a Q? Boy, that's confusing because Q is also, OK, yeah, they use Q, but Q is also the output of a flip-flop, but they also happen to use that as the output of the state machine. And that's it. That's the whole design. Assuming I didn't make a mistake there. Any questions about that? Now, unfortunately, I haven't figured out a way to ask questions like this on the quizzes because the quizzes are multiple choice. But on the test, on the exam, I will ask you to actually potentially draw a circuit or a finite state machine automaton, graph. So make sure you can do that. On the quizzes, I come up, have to come up with, I have to structure them as multiple choice. Okay, let's see. The next question is very similar, except this one is a Mealy machine. And I know that because they moved the output out of the states and onto the arcs, onto the transitions. So what does this one do? How is this different? Well, it's similar. I start at in S0, that's my reset state. If I get an A, I transition to S1. So if A is asserted, if in the next cycle B is asserted, then I'll jump to S2, right? But once I'm in this state, the only way to get Q is if I set A and B to 1 when I'm in this state. Right? So basically, this state machine allows me to accept a little bit more of a complex pattern. I'm looking for A to be asserted, B to be asserted, and then in the third consecutive cycle, I'm looking for A and B to both be asserted, in which case I'll pulse the output. And, also, right, and then, in fact, also notice as long as I hold those both asserted, I'll stay in that state. Make sense? So by building this as a Mealy machine, I can have a, everyone got that? I'm going to erase this. Have a little bit more of a complicated pattern. So let's look at, for this one, let's look at a timing diagram instead of building the logic for it. So let's see, I'll have a clock, a reset, okay, and then here's my reset. I'll do something here. I'll set this reset to be, give it a little pulse. Okay, and then I've got, I'm going to put a little marker here on all the rising edges so I can keep track of what clock cycle I'm in. Okay, so this is cycle 0, cycle 1, cycle 2, cycle 3, cycle 4, cycle 5, and cycle 6. Okay, so now notice the reset is not synchronized with the clock. And I did that deliberately because I'm going to assume that this is an asynchronous reset. So the minute this thing sees a reset, it's going to go back. So my state value is going to be is going to switch, right after it sees the reset. It's going to switch to S0, right? S0. You guys see that? So in other words, there's this, a lot of times you'll see these little arrows on these things. This means that there's a causal relationship here. Reset high, state resets, right? So that's why you could put a little arrow here to indicate that, to make it a little bit more obvious. Now I need to also have A and B on here, and I need to have Q as my output on here. Okay, so now as long as A is not asserted, then I'm going to stay in state S0. So let's say that A is 0 for cycles 0, 1, and 2. As long as that's the case, I'm just going to stay. I'm going to stay in there. In fact, I'm going to continue to stay in there because even if I were to change A right here, and this is the thing that sometimes is confusing about these timing diagrams. Notice that I changed A on the rising edge. Right? But what we expect to happen is when A gets asserted, we're going to switch. What's supposed to happen? We're supposed to go to state S1, right? But that didn't happen here. Why? Because I changed A on the same edge of the clock that I would have been looking at A. And when that happens, you generally assume that you're going to see the state machine is seeing the old value of A, not the new value of A. Right? Makes sense. Now you might say, why is that? Well, it's because the thing that's generating this A input is presumably another state machine somewhere or some logic that's also acting on the clock, right? And because of the propagation delay of the flip-flops and the logic for the output logic, it's guaranteed that whenever this A arrives at the input will be slightly after the rising edge, right? Hopefully after the hold time, right? You guys with me? In fact, just to make that clearer, I will move A a little bit past there. That's what the book does. In the diagrams in the book, whenever they change an input, they nudge it a little bit past the edge, right? You guys with me? Okay. So what that means is that it's going to take the state machine, will transition to S1 there on the following edge. Even if A drops at that point, A might drop at that point too. Right? So what's happening is that on this rising clock edge, right, I'm seeing A be high, which is going to cause me to transition to state S1. Right? Now once I get in there, what are my options? I could either go to state, well, I shouldn't say options. What are the outcomes? It'll either go to state 2 or it'll go back to state 0, but it's certainly never going to stay in S1 for more than a cycle. So I know based on the state machine that I'm going to have another transition there. The question is, where is it going to go? Well, that depends on B, right? So B, let's just assume B was 0. And let's assume that we're entering the correct combination. So the idea is that A has got to be asserted in one cycle, B has to be asserted in the next cycle, right? In order for us to progress towards unlocking this thing, right?
Determine how long B in S0 compares to B in S1.
Well, S0 is I'll be in S0 until I get an A. Until A becomes 1, right? In this case, I was in S0. Well, let me clarify that a little bit. I started out in S0 because of the reset, right? And then I stayed in there until I got an A, until I saw an A, right? An A.
Came in cycle 3.
Right. Yeah, A was, that's correct. That's right. Now, if, let's say A was asserted right from the get-go, right? Maybe A was locked in high. If that were the case, it would have transitioned here. Right? It would have still been in S0 for one cycle because when I reset it, I guaranteed that I'd have to be in S0 for at least one cycle. But if A was already high initially, then it would have only been in S0 for a cycle and then it went to S1, right?
Oh, I think I get it. It needs to be in one full cycle and then you can start putting in A and B and all
Right.
that.
Unless you don't put in A, in which case it'll stick around in S0, which is what it did here. It stayed in there for 3 whole cycles, right? Because I didn't get an A until cycle 3, and so so then B, let's say B went high here, goes low here, right? So on the next rising edge, I'm in S1, rising edge comes, I got to look at B. B was already high, and so I will transition now to S2. And again, S2 has a loop back, so I might stay in S2 or I might go back to S0. It depends.
Depends on AB.
Right, yeah, it depends on if A, B are asserted. Now the question is, when would A, B have to be 1 for this to work out for me? Well, they would have to be 1 on this rising edge. The problem is they're not. A is going to be seen as a 0. A is going to be sampled as a 0, and B will be sampled as a 0, right?
So that means they both go back to S0?
Yep, which means that I go back to S0, and I never get an output. Q is, and by the way, Q is 0 this whole time. Right?
It's always 0?
Always 0, yeah. Now, let's say I put the combination in right. The only way that would have worked is if A and B were both high in S2. And if that were the case, then A would have had a transition about right there, would have the transition in cycle 5. And B would have had to also, well, B could have just stayed high because it already was high, right? All right, now if that were the case, then I would have been in S2, rising clock edge. I would have seen 1, 1, in which case I would have actually stayed in S2, right? Now here's the thing though, because this is a Mealy machine, Q would have went high as soon as I got into S2. Yeah, the second I entered S2, right? Q would have gone high, so it would have transitioned high right there, because it's a Mealy machine, and all I care about in a Mealy machine is I got combinational logic that looks at the state and looks at the inputs combinationally, which means no waiting for clock edge if it's combinational logic. So the output logic is combinational, combinational function of the current state and the inputs. So I get into S2. And actually, that would not have been a change. That would just be a flat, right, like that. Right? I would have went into S2, and as soon as I got into S2, it would have recognized that A and B were both high. So Q would have actually went high right there, right? That's kind of like what it was in the old one, too, right? The old one also would have went high because Q. In the old, when I say the old one, the previous problem, the previous exercise, it was a Moore machine, and it had Q1 and S0, which meant that in this case, Q would have also went high as soon as you transitioned to S2, right? The difference is that in this guy, I could have also transitioned to S2, but never raised Q because it's a Mealy machine. You guys with me? So in other words, in a Moore machine, you're forced into assigning outputs based on what state you are. But in a Mealy machine, I have an option. I could have went into S2 and asserted Q, or I could have went in S2 and not asserted Q. It all depends on what my inputs were. That's why you put the outputs on the transition. You guys with me? Yes, yes. It depends on the clock only because it depends on the state, right? But aside from that, it doesn't depend on the clock. Like Q is asynchronous with respect to the current state and the inputs. But as soon as I'm in the state, right? So here's what you can do with a Mealy machine, right? Let's say I got into S2, and let's say I glitched. Let's say that A glitched. Let's say that A went down and then up. Say that happened, right? You would actually see that glitch translate onto Q as well. You would see Q do that as well, right? So this is why I say that Mealy machines have an asynchronous output, because if I got into S2 and I started glitching A and B before the next clock edge came and the state machine had the opportunity to leave S2, then you would see that happen over here, right? Does that make sense? Now, here's the danger is, what happens if the glitch happened right at the clock edge, right? Like let's say I was high, but then I temporarily went low. Let's say I did one of these numbers. In this case, when the clock edge comes, it would see A as being low, even though it was only low temporarily, but that would be enough for it to lose S2 and go back to S0. Yeah, because remember, as far as the state transitions go, they only happen on the clock edges. So the state machine only cares about what the inputs are on the clock edge, right?
Q would go back down to 0, right?
And Q, yes, and that's correct, yeah, because Q would also drop as well, because even though A and B are high, it's too late. I've already transferred back to S0, so now I have no way to do that anymore, no way to raise Q. Make sense? Yes?
So why is Q rising on clock cycle 5? Wouldn't it be doing it on
No, that's the difference. So as soon as I get to S2, once I get into S2, is this the right? Yeah. Oh, it's the right one. Yeah. Once I get to S2, I have the option of driving Q up or not, depending on what the inputs are, right? So what I mean is that see, the confusing part, the thing that used to confuse me about Mealy machines was I always think of transitions as being, transitions are like how you switch states, right? But actually, this one has nothing to do with transitioning states. All this one is that this one is saying that when I'm in S2, when A, B is 1, I want to have 1 Q, right? It's almost like having a little mini truth table inside the state is really what it is. But you use the transitions to also indicate state transitions, or use the arrows to indicate state transitions as well.
Okay, so if both A and B are 1, you can kind of ignore the 0 it gave you on the transition and follow that one instead?
Yeah, well, I have to be in S2.
Yeah.
Yeah, but yeah, once I lock into S2, as soon as I lock into S2, once I switch to S2, then I could potentially, raise that Q.
Okay.
Does that make sense? I don't know if I answered your question very well, but that's... Yeah, Mealy machines are usually you see more machines more often. Yes?
So, why would you go back to S0 here?
This was because for whatever reason, and this is kind of just a contrived example, but for whatever reason, A had a glitch here. What I was trying to show is that the transitions happen on the edges, right? So if A and B, let's say I wanted A and B to be high, but for whatever reason, A happened to be low at that clock edge, at that critical moment in time when a clock edge came, then it would cause it to go back to S0, right?
Is that saying A or, like A not or B not? Or going back to
Oh, this? Yeah, this is a, this is they're using De Morgan's law here. They're saying A and B, right? But if you say not A and B, then through De Morgan's law, that implies not A or B, right? That's all they're doing there. So this is, if A and B are both true, you stay in there. In any other case, you go back. All right, make sense? Okay, so that, let's see, there's, hopefully that clears things up a little bit with the Mealy versus Moore, also how to build the state machines and how to read and build the timing diagrams. That was a nice example because we could show all that stuff. The next topic in chapter 3 was the timing. So we talked about how flip-flops have a setup and hold time. You have to make sure that the D input into a flip-flop is stable for the setup before the clock edge, and it's stable for hold after the clock edge, and together those are called the aperture. This is the only way to guarantee that the flip-flop behaves correctly. If you violate this aperture, and thus violate what the book calls the dynamic discipline, you can put the flip-flop into a metastable state, which will eventually resolve, but it will take an amount of time that is difficult to predict. So they model that time as an exponential distribution, right? So now, if you don't violate that time, if everything is working properly and it's not metastable, then you can associate a contamination delay and a propagation delay with a flip-flop. So flip-flop is kind of like a gate in the sense that after you get the positive edge, and by the way, these are relative to the clock edge, right? So don't be confused. When we talked about contamination and propagation delay with regard to gates, it had to do with whenever you changed the value of an input to the gate. That was the time that was the time in which we were measuring the contamination propagation delay from, right? The time that you change an input to a gate, and there's some time that elapses where you'll see some activity, and then there's a little bit longer time that'll pass where the output will be guaranteed to be stable. The contamination and propagation delay with regard to these flip-flops has to do with the clock edge, right? Okay, so from this, you can start to calculate things like the maximum clock period. So the maximum clock period is simply the propagation delay plus the propagation delay of the actual flip-flop plus the propagation delay of the combinational logic plus the setup time, because you have to make sure that the input of this is actually stable before the next clock edge to satisfy the setup delay. You guys with me? So this, I think this is pretty straightforward. The contamination delay, though, in the hold time constraint is a little bit trickier, I think. Because in this case, this has nothing to do with the clock at all. The propagation delay was a notion that had to do with the clock period, right? Whereas the hold time has nothing to do with the clock necessarily. It's you need to make sure that the contamination delay of the data path, where the data path is register to register, doesn't violate the hold, right? So in other words, when you change something here, that'll cause a change in the output of the flip-flop after the contamination delay, and then the logic will see that, and then the logic will update its outputs after its contamination delay. And if that time that output from the logic arrives too soon, too fast, if it's too fast, if it gets there too fast, you'll violate the hold time. Does that make sense? Okay, so to check that, you just have to add the contamination delay of the flip-flop plus the contamination delay of the logic, right? That's it. You just add those two. And you need to make sure that that number is greater than the hold time. And if it's not, then you have to add some stuff, add some delays in there, add some logic to slow it down. Okay, so this gets a little bit more complicated, though, when you have to consider clock skew. Because before, with this slide, we were assuming that all the clocks, all the flip-flops are seeing the clock edge at the same time. But in reality, you don't, because the clock network is huge because it connects to every flip-flop on the chip. And because it's so big, it has a lot of capacitance. There's a lot of metal that has to be charged and discharged every clock cycle. And so you have this clock skew. It's unavoidable. Meaning that one flip-flop may see a slightly phase-shifted version of the clock as compared to another one on the same chip. So to account for that, you have to incorporate the clock skew into this propagation delay as well. So in this case, you're saying, well, this flip-flop may, this flip-flop, in order to satisfy its setup time, it's going to have to get its inputs, or the time that it sees its inputs is going to be the propagation delay of this guy plus the propagation delay of the logic plus its setup, right? So that's the amount of time you have to be in there minimum. But you have to also add the skew as well, because this clock might be, see, I always forget this. The edge of this one might be sooner than this one, right? So in other words, the rising edge of this clock may be happening, maybe phase shifted to the left, sooner to this one, right? Which basically means that the clock period you have for this data path is shorter than what you expect it to be, right? Does that make sense? In other words, there's this compression effect because you might have a gigahertz clock, which gives you a nanosecond of clock period. But if this clock happens to see its edge sooner than a nanosecond relative to this one because of the skew, then in fact you have less time, right? Meaning that you have to make sure that your clock period accounts for that. You guys with me? Not sure how well I explained it, but yeah. In other words, you just add the setup time to the path time, right? Okay, then you get to the hold time. The hold time is the opposite, because in the case of the hold time, you're considering the worst case scenario is when the edge of this clock is phase shifted the opposite direction relative to this. So you're thinking, well, what happens if this clock edge might be later than this clock edge? You guys with me? So that would mean that the input, this D2 input, might appear to arrive sooner, right? Possibly violating the hold constraint, even though you didn't really violate it, but you violated it according to when it sees its clock, right? So in that case, you have to put the skew over on this side of the equation, right? So in this case, it's the hold. It's the hold plus the skew. So the contamination delay of the flip-flop plus of the you add the logic contamination delay must be greater than the hold time of the flip-flop plus the skew. So just I want to point out that you got the skew is on this side of the inequality with the hold time, right? Okay, I think I had an example of that too. 3.34. Let's take a quick look at that. 3.34. I thought that was a good one. What's that?
Another one that wasn't assigned in our homework.
3.34. Oh yeah, so you are designing an adder for the blindingly fast 2-bit repentium processor. The adder is built from 2 full adders. So it's the carry out of the first adder is the carry in of the second adder, shown in figure 3.35. Yes, this is on the quiz. I changed the numbers though for the quiz, so be aware of that. So anyway, the question is, if there's no clock skew, what's the maximum operating frequency? So how would you solve this? Well, you just take the propagation delay of the flip-flop, and you would have to add it to the propagation delay of the logic. But that's the question. What is the propagation delay of the logic? How do we figure that out? You have to find the maximum path through this, the highest, the critical path. The critical path might be from A or B to S into here, or it could be from carry in to carry out, or actually it could be A, B, carry in, any of these to carry out, and then you would have to add that to the delay from carry in to the output here. Right? You guys with me? Okay, so you would have the propagation delay, and then you would add the setup time, and then you could get the frequency. Right? How much clock skew can the circuit tolerate if it must operate 8 gigahertz? Well, 8 gigahertz would be 125 picoseconds for your clock period. That would be your TC. So you have to subtract from 125. You'd have to subtract your propagation delay from this flip-flop through the logic, and then whatever's left over is your in the setup time for this flip-flop, and then whatever's left over in that 125 nanosecond budget would be the most clock skew it could tolerate. Everyone with me? So so the question is, we have 125 picoseconds, right? And that must be actually greater than or equal to the propagation delay of this guy, which is 35 picoseconds. So that's, what is the, yeah, that's the propagation of the flip-flop, plus whatever the delay of the logic is, which is, I believe on this one, I think your maximum delay here, hopefully I don't screw this up, A or B to C out is 30 picoseconds. So going from A to B to C out is 30. Then the C out of this guy goes into this one to C in. So you have to take 30 and add it to,
It's all the 20.
is it 20? Yeah, so it's 50 in total. So 20 from C in or C out to sum, 25 from A, B to C out, and 30 from A to B to sum. Right, so in order to get C out, I need 25, right? I need 25 to get to C out, 25 picoseconds, right? I mean, there's also C in to C out, but that's shorter, that's 20. I want to take the, so I have two options, 20 or 25. I'm going to take 25 because that's the longer one. I'm trying to find the worst case delay. So 25 is the worst case delay to get to C out. And then once I come out of C out, I go to C in on this guy, on the second adder. And from C in to either output is contamination, sorry. And from C in to C out, 20. 20. So what's the total, 45? Yeah, I got 25 to get the C out, and then from C in to sum on the second adder would be another 20. So it would be 45, right? So that would be 45 plus the setup time. What's the setup time?
What do you have to, like, you have to consider from C out to C in? Like, so you would go, so you would go from C in to C out, then do you have to consider the next transfer between the adders? Or the...
Well, it's whatever the maximum delay is from, it could come from C in. The maximum delay actually could be from C in on this guy, propagating through here to C out.
I guess the question is, when you're calculating the time, you would go from C in to C out, but then do you have to make that transition from C out to C in and have that in there as well, or is that just negated? So going from...
You mean the delay of that wire?
Yeah.
No, there's no delay of the wire.
Okay, so
Yeah.
it's just the two.
Yeah. I mean, there could be wire delay, in which case you would have to, you'd have to include it, but it's not listed here. So assuming that this is really, really fast, yeah. Yeah, by the way, this is something that, this is a full adder. This is the problem with full adders. You got to propagate through the carry chain. That's why no one really uses full adders in reality. Too slow. Okay, so then you have the setup time. 30, right. So you add 30, and then you have plus skew. Right? So the skew must be less than or equal to 125 minus 35 plus 45 is 80, minus 30. Right? So that's 125 minus 110, right? So 15. 15. So skew must be less than or equal to 15 for this to work at 8 gigahertz. Assuming that I did the propagation time right, I believe I did. This was hard to read because I put everything. In the quiz I bulleted it, so it's easier to read all the numbers off of there.
So did you get 125 picoseconds from doing 1 over 8?
1 over 8. Yeah, that's right. Yeah, they always give you clock speed in terms of the rate instead of the period, so you have to take the reciprocal. Okay, there's another question that'll say, how much clock skew can it tolerate before it is a hold time violation? Well, for that is the hold time violation would happen if the hold time for the thing is, anyone know? Scroll up. The adder. 10, your adder has, the adders, each full adder, the adders, each flip-flop, yeah, right, 10, right, okay, so 10. So the hold time is 10 picoseconds, which must be greater than, right, because I got to go beyond, I got to hold it for 10. And that's going to be greater than the contamination delay of the flip-flop, which is 21, right? Plus the contamination delay of this guy, which is probably just A to B to S, I'm assuming. The adder has a 15 from either C in to either output. So it looks like 15, yeah, 15. Because that's the smallest contamination delay, right? But the skew is subtracted from that, right? Right, in this case, because you might look at this and say, well, 21 plus 15, oh, we're fine. I mean, that's way beyond 10. That's no problemo. But the skew will act to reduce that, right, is the problem. So that's the part of this that's, so in this case, the skew, let's see, does that make sense? Did I do that right?
Wait, the whole time is supposed to be greater than?
The whole time has to be, we want the contamination delay that we experience has to be greater than the whole time. The whole time is a minimum, right? Now the question is, and this is the part that always trips me up, the skew could potentially subtract, right? Yeah, right. Oh, sorry, this would have to be greater. Yeah, the actual contamination delay must be greater than the whole time. Yeah, sorry, you were right. Thank you. I had that wrong, right? So what that means is that so we would take the 21 plus 15 is 36, and we would subtract 10 from that, right? Which would be 26, right? And then we'd have skew must be less than 26, right? Right? So before it was what, 10? So actually the skew is more constrained under the setup time than it is the whole time in this case, right? Any questions? All right. Okay. Almost out of time. I had one more example. I didn't. I'm just going to briefly. I wanted to look at 3.36 here. So finally, we talked about synchronizers. We also talked about parallelism. There's an example on the exam on the quiz for parallelism. If you have any questions about that, let me know. The synchronizer is asking about mean time between failures. So the idea with that is that you have a probability of failure the probability of failure is the T0, which is a parameter, divided by Tc, which is the clock period. And then you multiply that by the exponential of minus t divided by tau, where tau and T0 are given to you, right? Now, if you're talking about a synchronizer operates by putting two D flip-flops in series. And the idea is that if the first D flip-flop is metastable, you're going to try to bet the odds that it will stabilize in time for the next clock edge, so the second D flip-flop can capture that and synchronize it. You guys with me? So in that case, this time up here, this time is actually going to be the clock minus the time, right?
Now, will this equation be on the test for us to utilize, or do we have to map?
No, you want to know this one.
All right.
Okay? So So TC minus T setup. Sorry, TC minus T setup. There, actually, right? So the idea is that this gives you the probability of failure, this instantaneous probability of failure, right? In order to convert this to a mean time before failures, you just calculate this and then you invert it, right? So the mean time between failures equals 1 over the probability.
Now, out of curiosity, what is tau in this situation?
Tau is given to you. It is a technology parameter. Like whenever you're making a new chip, you get all these parameters. It's part of the semiconductor technology, right? It comes from the fab guys and the guys that give you the technology libraries. So this T0 is given to you. Tau is given to you. T setup is given to you, right?
But you need to find TC.
Well, it might ask you to solve for TC for a given, for a target failure, target probability, or target mean time between failures, or they'll give you the TC and say calculate the mean time between failures, right? Now this is going to be in seconds, though. Keep that in mind. So if this number is huge, and you want to express it in terms of hours or days, you're going to have to adjust. You're going to have to convert it, right? You'll get seconds for this. Make sense?
It does.
Okay. So make sure you remember that. The way I remember it is, T0 is given to you, so that goes on the numerator here. And then when you look at tau, it's in the denominator over here, right? Notice? So of your two parameters, the first time you see it, it's in the numerator, and the second time you see it, it's in the denominator, right? That's the way I remember it. Yes, so any other questions?
What is NT?
Mean time between failures. So that's how long you can expect to be able to go before there's a failure, meaning that you get a metastable result out of the second flip-flop. A failure, by the way, let me clarify that. A failure means that this second flip-flop goes metastable, meaning that you don't get a clear outcome here.